to recap that bluket, if you are multiplying bases like x to the second times x to the sixth, what do you do with those exponents? You add them. Multiply means add the exponents. If you are dividing, what do you do with the exponents? Subtract them. This is going to be x to the, wow, I almost forgot how to subtract 6 minus 2. And if you have a power raised to a power, you're going to multiply the powers. This would be x to the 12th. It looks like it's distribution. It's not distribution, but it kind of feels like it. Okay, those are our basic exponent rules. If you're multiplying, you add. If you divide, you subtract. If you have a power raised to a power, you multiply. Kind of spells out the word mad spam. I don't know if you ever heard that acronym before. MADSPM are my exponent rules. Multiply, add, divide, subtract, power to a power, multiply. The only other one we have left is this one where we changed it. Well, there was the negative exponent rule, but I think we got that. What happens if we have a fraction exponent and I want to rewrite it in radical form?
The denominator is the radical.
Yes, the denominator is the index on the radicand, and the numerator stays inside. In Algebra 1, we use this acronym to teach this called TIBO, where it says the top number goes inside, so top number inside, and the bottom number goes outside, bottom number outside, TIBO. Top number in, bottom number out. And vice versa if you're trying to rewrite it the other direction, okay? Those are our basic exponent rules that we kind of need to remember to be able to go for logarithms. Since logarithms are the inverse of exponentials, these rules are going to come back to haunt us today. Now, our goal today is just to be able to transform and evaluate logarithmic expressions. A lot of this stuff you cannot do with a calculator because the calculator only thinks in base 10 or base E, and we're going to be using other bases. So it's going to be very important that we know how to do what's called the log loop, or rewrite logarithms as exponentials, because we can think in exponentials, our brains, more easily than we can think in logarithms. So if we want to rewrite a logarithm that has a base b, you're going to keep the base the same. We kind of went over this last time. All you're going to do is loop the x's and the y's since they're inverses. So the y is going to go where the x was, and the x is going to go on the side where the y was, over here. It's called the log loop. Yes, the x now becomes an exponent when it was something that was equal to, and the y was a part of the logarithm, and now it's set equal to itself. That's fine, but it's this loop. You loop the numbers around, the base stays the same. So whatever base the logarithm is using, keep it as the base of the exponent, flip-flop the x and y, called the log loop. So let's just practice that for a little bit. Rewriting the expression as a logarithm, the base stays the same. So if I was rewriting 2 to the 5th equal to 32, a same expression would be a logarithm with a base of what number? 2. So log base 2 of the number 32 would be equal to 5. I've looped them around. Base stays the same, but I looped them so the 5 comes on the other side of the equal sign, and the 32 goes on the other side of the equal sign next to the logarithm. It's called the log loop. Okay, even if the base is something ugly like 0.5, I mean, it's not that ugly, it's a half, we can still rewrite this as a logarithm. The log with a base of 0.5, so log base 0.5 of 0.125 is equal to the number 3. Base stays the same, and you loop the x and the y. You loop the top and the equals number. Do we see that? Rewriting it in the other form. We can go the opposite direction as well. If we started with a logarithm, we can rewrite it as an exponential. What's the base on letter A? I don't see a number here for the base. What's the base? Ooh, that's for a log with nothing showing. What kind of logarithm is that? Wait, what is this called? ln, what is that called? Natural log, meaning the natural number needs to be its base, which is what letter? E. So the base here is E. That's going to stay the same, and I'm going to flip-flop where the x and the y are. So that means the exponent is 5, And the approximately equal to number is going to be 148.41. Approximately equal, because we had to round that number, it would be, you know, an ongoing decimal. So when you round a number today, I would like for the equal signs to be squiggly because they mean approximately equal to, telling me you rounded. Again, all I did was flip-flop where the x and the y are using the log loop. Can you guys try B? Just rewrite it as an exponent, please. Okay, what's the base here? 1/2. Now I'm going to put 1/2 in parentheses because I want to make sure that my exponent actually reaches the whole 1/2. But the exponent we're going to use is the number -5. And we're going to say that that's equal to 32. Now this is the first one that personally my brain kind of makes sense of. E to the 5th power, I can't multiply by e in my head because it's a decimal, repeating decimal, or an ongoing decimal, a rational number. But 1/2 to the -5. Let's just explore that for a second. In our blue kit, we couldn't have negative exponents. So what would I do with that 1/2 to make it have a positive exponent? Flip it over. So then it would be 2/1 or 2 to the 5th power. Well, what is 2 to the 5th power? Yeah, 2 times 2 times 2 times 2 times 2. This is 4, 8, 16, 32. This is actual things that we know. We can write it as a logarithm with this base or as an exponential, but we're just calculating numbers today. Now that idea of calculating numbers, figuring out what the base requires to be able to be multiplied out, is how we're going to tackle these next couple questions. We're going to evaluate each expression without a calculator. Now the way that we do this is we want to get the bases to match so we can compare exponents. Now right now this logarithm does not have a number that it's equal to, so we're going to let it be equal to some variable x. I can't think in logarithms, but I can think in exponentials. If I were to rewrite this with the log loop, it would be a base of 5, a power of x equal to the number 125. I can't compare these two numbers until the bases are the same. Can we write the number 125 with a base of 5? Meaning, is there a way I can multiply 5 by itself and end up getting 125? Yeah, isn't 5 to the 3rd power 125? 5 times 5 is 25. 25 times 5 is $1.25, or 125. I think about it in quarters. Okay, so if that's the case, now that the bases match, I can literally just compare the exponents so that x is equal to 3. That's the evaluation of this logarithm without using a calculator. Log base 5 of 125 is equal to 3 because 5 to the 3rd power is 125. So the goal of these problems is to get both sides to have the same base so that then I can compare their exponents. But you have to get creative in how you get the bases to match because sometimes it's not as straightforward as 5s. Okay? Okay, so we've done that first example. So let's go to example B. Again, we want to evaluate this logarithm without a calculator. So we set it equal to x and try to figure out what it's equal to. That would be evaluating. This is like plugging in a number evaluating. We're just trying to figure out what comes out of it. That's what we're doing here. But to do this, we're going to use the log loop to rewrite this. 7 to the x power equal to 1. Okay, we need the bases to match to be able to do this. So can I write the number 7 or number 1 with a base of 7? I heard someone say it. So anything to the 0 power is 1, correct? So if I write 7 or 1 as 7 to the 0 power, I can compare the 7s and say that x is equal to 0. Yeah. And I'm done. So log base 7 of 1 is equal to 0. That's the game you play with these. So depending on what the base is, you try to get the bases to match. If we go to C, what's the base here? Oh, this one actually says log. E is going to be the base for the ln one. What's the base here? 10. This one's the common logarithm, so this is base of 10. Base 10 raised to the x power, because we're going to set it equal to x, should be equal to 0.01. All right, well, I need those bases to match. So we have to do some creative thinking here. Before you get your calculators out, how do you write 0.01 as a fraction?
1 over 100.
1 over 100. Do you notice now that they can have kind of similar bases? Because can't I make 100 out of 10? Yeah, this would be like saying x to the 10th is equal to 1 over 10 squared, right?
Yeah.
Because 10 squared is 100. But I don't want it to be 1 over 10. How would I make that to where it's just a base of 10? 10 to what power is the same as 10? Negative 2. Oh, look. Well, now the bases match. I have 10 to the x equal 10 to the negative 2. So very simply, I can just say x is equal to negative 2. So log base 10, or the common logarithm of 0.01, is equal to negative 2. So with these problems, you do sort of have to just get creative with how you're solving these questions. Get the bases to match, and then you can compare the exponents. Okay, for number D, letter D, we're going to go ahead and do the log loop, but I also want to remember what we talked about at the beginning of class with rational exponents. So we're also going to rewrite square root of 2 so that it's a base with a power. Okay, if we were to log loop this, it would be 8 to the x power equal to 2 to the what power if I were to rewrite square root of 2 as a rational exponent? 1/2. Where did that come from? So there's an invisible 1 and an invisible 2. You've always called that shape a square root, square because 2, so its index is 2. So that's 2 to the 1/2. Okay, I want these bases to match. I need these bases to match. So I'm going to reduce this number 8 so that it's written as a base of 2. Because isn't 8 2 to the third power? So if I change this and I say 2 to the third power to the x power is equal to 2 to the 1/2. Because 8 is just 2 to the third power. We have an exponent rule that we reviewed at the beginning of class that says, what can I do with these power to a power moments? Multiply. So this is going to be 2 to the 3x equal 2 to the 1/2. Do my bases match? The big numbers? Yeah, once the big numbers, those are the bases. Once those match, I can just compare the exponents. I now have 3x equal to 1/2. Divide by 3 on both sides. This would be x equal to 1/6. Let's try this next one for you guys. I want you to try E. Log base 36 of 6. So flip it first with the log loop, and then try to get the bases to match. Is this what you guys got? So we do the log loop, 36 to the x equal to 6, which is 6 to the first power. I notice that I can write 36 with a base of 6 if I just make it 6 squared. Once I make this 6 squared so that the bases will match, this would be 2x. Comparing the exponents now, once the bases match, 2x equal to 1, divide by 2, you get 1/2. So log base 36 of 6 is 1/2, which makes sense. Because if we wanted to check our work, we take this number and we put it in there as x. 36 to the 1/2 is basically square root of 36. What is the square root of 36? 6. So this checks out. So if you're not sure you're getting these problems right, what you do is you take your answer, whatever you got for x, you plug it back in here to see if you actually get the right number out the first time you've done the log loop. Okay, I want you to try F as well. Try that one. Okay, so to get creative with this one, we needed to remember the relationship between the number we see on the left side, which I know is a third, but really that's 3 to the negative 1. So the base would be 3. And 81. 81 is 3 to the 4th power. 3 times 3 is 9, times 3 is 27, times 3 is 81. So if I put them with bases of 3s, I would have 3 to the negative x, distributing x. Not distributing, you know what I mean. Multiplying them. 3 to the 4th, so then we compare the exponents. We have negative x equal to 4, or x equal to negative 4 when we solve it. Okay, we'll do G together. The numbers I have in G are 1 over 64 and 32. If I do the log loop, the base would be 1 over 64 equal to 32. I need those bases on the left side and right side to end up being the same. Does anyone know how 32 and 64 are related? I know you can divide them, but like what power? Powers of 2, 3, 4, 5, 7? Not multiply divide, but powers. Not Austin powers. No, even easier than that. 2. If we think about it, we can recognize 32 maybe a little bit easier. 32 is, so 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 32 is 2 to the 5th power. If I do that one more time, 2 to the 6th power, so 32 times 2, isn't that 64? So I'm recognizing numbers 32 and 64 are part of the powers of 2, so I want to use the base 2. But 64 is in the denominator, so I'm going to first move it to the numerator, and then I can rewrite it in base 2. 64 is the same as 2 to the 6th power, and since it was in the denominator, I make that negative. I would multiply those powers together. That's the power of a power rule. 2 times negative 6x equal to 2 to the 5th power. I can now compare my x values. I'm going to do it on the side because I ran out of room. Negative 6x equal to 5. Divide by negative 6. We'd get x equal to negative 5/6. And again, if we were not sure, we can take this value of x and plug it in right here to make sure that 1/64 raised to the negative 5/6 powers is 32. It's kind of a game you have to play with yourself of how are the numbers related. What power do I need to use? So if we're playing that game with H, I see the numbers 729 and 81. I don't currently recognize 729, but do you recognize 81 as a power of something? It's 9 squared. It's also 3 to the 4th power. Fun fact. So we could use bases of 9s, or we could use bases of 3s. We'll use bases of 9 since that's what you recognize first. If we log loop this, it'd be 729 to the x power equal to 1 over 81. You recognize 81 as a power of 9. So let's see if 729 is also some power of 9. If you don't know it in your calculator, do 9 times 9 times 9 times 9, as many times as you get until you get 729. Shouldn't be that many. How many is it? 3. So 9 to the 3rd power is the same as 729. And 1 over 81, if I write that as a power or a base of 9, would be 9 to the negative 2 power. You could have done this problem with bases of 3, but we recognize the base 9 first, which means go with base 9s if you recognize it. Once the bases match, we just compare the exponents. 3x equal to negative 2, solve for x. X is equal to negative 2/3. Again, we shouldn't get these questions wrong because we can take this number and plug them back into the beginning exponent version and make sure it actually comes out to 1 over 81. Okay, we can do this also with bases that are just letters, so not actual numbers here. We can still do the same process. Log base a of 3, the 3rd root of a to the 4th power. If we log loop this, this is going to be base of a to the x power equal to the 3rd root of a to the 4th power. When we did the Blue Kid at the beginning of class, we had these types of radicals and we rewrote them as exponents. What would be the exponent for that? A to the 4/3. Do the bases match now? X equal to 4/3. Okay, for the first one, I don't have a base showing. What's the base? 10, because it's a common logarithm. So we do 10 to the x power equal to the fourth root of 10. But if I remember to get them to be the same base, I would like for that second one to not be in radical form. I would like for it to be in fractional exponent form, rational exponent form. So this, if I rewrite it, is 10 to the what power? 1/4. So x is just a fourth. And the next one's also very similar, because what's the not showing base for ln of 1 over e? E. So we're going to do e to the x equal to 1 over e. But if I want them to have the same base, that means I want the e to be not in the denominator. I want it to be in the numerator. That would be e to the negative 1 power. Once the bases match, x is just negative 1. So the natural log of 1 over e would be equal to negative 1. So that's evaluating logarithms without the use of a calculator, because your calculator only has a button for log base 10 and log base e, which means we probably could have done the last two in the calculator, because they would log 10, base 10 and log base e. But the rest of them, when they're different bases, we can't use the calculator for them, all in the brain. So we rewrite them as an exponential and solve them that way. Okay, so some more properties of logarithms. This is a consequence of the fact that the inverse of logarithms is an exponential. We have two pretty important things here. What do you notice about the two logarithms in the little box up there? Maybe specifically noticing stuff like this. What do you notice? This first one is an exponential, and in the exponent is a logarithm with what? That's the same number, right? Same letter? So we're raising an exponent to a logarithm with the same base. Basically what happens is these cancel out and you're just left with m, whatever was inside the logarithm. Because they're inverses of each other, they're going to undo each other. An exponent with the same, or exponential with the same base and a logarithm with the same base cancel each other out. And vice versa. So here I have a logarithm with a base b. Inside the logarithm is an exponential with a base b. Those essentially cancel each other out and you're just left with this exponent. So logs with the same bases as the exponentials, when they're tucked inside each other, are inverse operations. They cancel each other out. So if we look at these, we should be able to do these very, very quickly. Log base 6 of 6 to the third power. Since these bases are exactly the same, it's going to cancel those out, and this would just be equal to 3, whatever's left over, essentially. On B, log of 10 to the 5th power. This should be very simple, because a logarithm with no base showing has a base of what? 10. And then I have an exponential with a base of 10 inside of it. Those are essentially going to cancel their inverse operations, and I've got 5. That's it. So how about E raised to the natural log of 5? What would it be equal to? 5, because these technically have the same base. E to the natural log's base is e. Those bases match, it cancels out. You've got 5 left. What about this one? What is this equal to? 7. Very good, because the bases match. We can essentially cancel them out. They're inverse operations. We've just got 7. Great. I love that property of exponentials. It's going to really, really help us when we start solving these types of equations next class. But also what's going to help us solve the equations next class that we'll deal with is these properties of logarithms. This is essentially the same properties of logarithms that we used for the properties of exponentials. When we were multiplying bases with exponents, what did we do with the exponents? Look what we're doing here. We're multiplying these bases inside this logarithm. So multiply means add. When I was dividing the bases earlier, what did I do with the exponents? Subtract. I do the same thing with logarithms. And when I have a power raised to a power, or a logarithm with a power on the inside of it, what is it saying I can do with that? Multiply. I also like to draw this little arrow boop, on these, So let me know that I'm taking that exponent, yanking it off, and putting it in front. So the exponent rules still apply for logarithms. If you're multiplying inside of a logarithm, you can expand it by adding, or vice versa. If you're adding, you can condense it by multiplying. If you're dividing, you can expand it by subtracting, and vice versa. If you have a base or something inside the logarithm raised to a power, you can yank it to the front, multiply it. And so we're going to work on expanding and condensing the different logarithms using these properties. So this first logarithm, base 10, we want to expand it. So I look at the inside and I decide what I'm multiplying or dividing. Don't worry about the power yet. We'll deal with that second. But right here, I am multiplying x times y to the third power, correct? That means this is going to be a logarithm of x plus a logarithm of y cubed. Because I was multiplying those two things inside of the logarithm, I can add them. Then I have this power here of 3. I can take that and I can multiply it in front of the whole logarithm. So the expanded version of this logarithm is log of x plus 3 log of y. I bet you're wondering why I lost the parentheses. If there's only one thing inside of the logarithm, we understand that this is inside the logarithm and that this is inside the logarithm. You can put these parentheses here. It doesn't change the problem at all. It's the same thing. It's like as if you were putting parentheses around an x before you squared it. It's not necessary unless there's extra stuff inside. Then you have to put the parentheses. So up to you on whether you put the parentheses or not when there's just one thing inside of it. So we've expanded it. Again, we expanded by adding when we were multiplying, and then we took exponents to the front. Make sense? Let's have you guys, nope, I'm not gonna make you do that one on your own just yet. Changed my mind mid-sentence. We'll do B together. Just by looking at what's inside of here, we are multiplying two things on top and multiplying two things on bottom. So we need to expand it slowly. I'm going to start by expanding the division bar. So if I were to just take the division bar and expand it there, this would be logarithm of x squared, and I'm going to change this to q to the 1/3. Do we know why it's q to the 1/3? Yes. Cube root, top number was 1, bottom number's 3. Okay. And then I'm going to subtract the logarithm with the base. So, sorry, the denominator. Y and then t to the 1/2. Again, do we know where the 1/2 came from? Yeah. The square root, there's a 2 right here as an index and a 1. So 1 top, 2 bottom. Okay. So I've separated it top and bottom. But then inside both of these, I still have a multiplication problem. So I would expand it one more time. This would be the logarithm of x squared plus the logarithm of q to the 1/3 minus the logarithm of y and the logarithm of t to the 1/2. Why do I need these parentheses here around the second term? Sort of.
Oh, because you distribute?
Yeah, we're subtracting this whole denominator, right? Because both of these were in the denominator. So I need to make sure I'm still subtracting the whole denominator when I'm expanding it out. I'm going to do two things at once in this next step because I ran out of space, and I'm sure you did too. I'm going to distribute this -1 to both of the things inside of that parentheses. I'm also going to use the rule that says anything with a power can come to the front. So I'm going to put that right there, and I'm going to put that right there, and I'm going to put that right there. I'm going to do all that in one step just to clean this up. We would have 2 log of x plus 1/3 log of q minus log of y minus 1/2 log of t. Whoa. Let's take a pause here. So C is for you. expand this logarithm. You got it. You got it. Okay, wait. Here's my hint for you in case you need this. I don't know if that hint helps you. Does that hint help you? Everything that's multiplied should get added. I'm going to help you out with the first step in case you're like, I didn't even get started. Okay, if I keep going on this one, here's what I would notice. I would notice I have these exponents that I can bring forward. I also notice that 6/3, that's 2. So I can write this as log base 3 of 81 plus 5 log base 3 of x. It's a weird looking plus sign. Plus 2 log base 3 of y. But I will tell you, if you were to stop here, it is not as expanded and simplified as possible. Did anyone notice that there is only numbers here? Log base 3 of 81 is all numbers. If we do what we did on the front page here and we say log base 3 of 81, that's a base of 3, some power equal to 81. 3 to what power is 81? 3 to the 4th power is 81. So that whole part right there actually becomes 4. So if you have whole numbers that you know you can solve or simplify with the stuff we did on the front page, you go ahead and do that. Log base 3 of 81 is equal to 4. So we can reduce that and simplify that. Okay, D is also yours. There will be something that reduces out in D, so I'm telling you to look out for it, but it's much easier than this one. I'm going to start showing this one on the board if you got stuck. Okay, so when we do this one, we would break it apart at the division and then break it apart again at all the multiplication. Hopefully you noticed that natural log of e is just going to cancel out. No, normally we were letting it be the exponent. There's no exponent showing here, so what is the invisible exponent? 1, which is why this turns into a 1. Now, I'm assuming a question that you're going to have is, Ms. Quigley, that's only numbers as well. Why didn't we multiply that out like we did log base 4 of 81 or log base 3 of 81? It's a great question. This is base E. Base E is a decimal. It's not something I can very easily do in my head to find one of these equal to 6. It's going to be some fraction, not a nice pretty whole number, so we don't do that part. But when they're nice pretty numbers, like we got 4 in part C, we would go ahead and do that. When it cancels out, it's always going to become the exponent. Let me write this a little bit better. If there was an exponent here, it would be the number 1. Whatever the exponent is, if it was a 5, I would have wrote 5. If it was 16, I would have wrote 16. But it's invisible, so it's 1, which is where the 1 comes from. That was a good question. Okay, so we've expanded these. Let's work the other way. We're going to condense them into a single logarithm. So we're working the opposite direction. We want to start with making exponents first. So all of these numbers that are in front are going to go up and be exponents. Don't worry about the signs yet. Just take the numbers forward, or take the numbers up there. If I just rewrite that much, this would be natural log of x to the 3rd minus, bless you, natural log of y to the 1/2 plus natural log, I don't know why I wrote natural log of z to the 5th. Well, that's the first step. We need it to be one single logarithm. Like I should only write ln one time to know that I'm done. So here's what I'm going to do. I look at natural log, and anything that is positive goes in the numerator. Anything that's negative goes in the denominator, which means this would be x to the 3rd power in the numerator, y to the 1/2 in the denominator, and z to the 5th in the numerator. Because positive things was multiplied in top, negative things, we subtracted the stuff in the denominator.
So where we go in order?
Like doing it in order, you can, or you can select all of the positive things to write them down first and then all of the negative things in the bottom. I like going in order because then I'm like checking it off a list essentially. Okay. If we look at B, again, the first thing I want to do is put the powers back up on top. So any of the powers I'm going to put back up. Undo the power of a power rule, essentially. Don't worry about the signs just yet. Just take care of this part. The next step in this problem would say natural log of x to the 3rd minus open parentheses natural log of y to the 1/2 plus natural log of z to the 5th power. All I did was take the numbers, the coefficients in front, and make them powers again. If we do what we just said, where we have one natural log and anything that's positive goes in the numerator, anything that's negative goes in the denominator, well, that x to the 3rd power is definitely positive. But then this negative is affecting both of these terms. So they both go in the denominator. So I'd have y to the 1/2 times z to the 5th because they're added, which means I'm going to multiply them. So the difference between A and B in putting two things in the denominator versus one thing in the denominator, do we see the difference? This is only subtracting the y to the 1/2 natural logarithm. This is subtracting both, so both went into the denominator. Do we see that difference? All right, let's do part C. What's the first thing I take care of when I'm simplifying or condensing? That. Take the coefficients and make them exponents. Great. So I have the logarithm base b of 27 to the 4/3 power minus the logarithm base b of 9 to the 2nd power. I noticed something about this one. I noticed that I only have numbers. What is 9 to the 2nd power? 81. So if I just change this to 81 for a second. And then in your calculators, because I'm sure you won't want to do this in your head, can you do 27 to the 4/3 power? Also 81. I could keep going and I could condense using logarithm rules, which means I would divide these. I'd get 81 over 81. That's 1. But I'm probably less familiar with logarithms than I am with just good old-fashioned combining like terms.
Ooh, they cancel.
They cancel each other out. This is 0. The logarithm of 1 is 0, but I'm not sure that we're as familiar with that fact as we are with combining like terms. So if you can get them to be like, they still cancel each other out, just like terms do. But everything has to be the same. If the bases were different, they would not cancel. If the number was different, they would not cancel. They had to be exactly the same. Okay, letter D is for you. Okay, I hear wait what, so let's wait. I took this 2 up, right?
No, I see that.
Okay.
But L send line. Natural log.
Great, that's a great question. So remember, once we have it all with no coefficients, so we have the exponents back. First of all, 6 squared, that's 36. We all see that, right? Okay. Anything that's subtracted goes in the denominator. Anything that's positive or added will go in the numerator. But we're multiplying them. When we had letters, we just stuck them next to each other because that means multiplication. But with regular numbers, I just can't write 4 next to 18 because it would look like 184. So I'm actually going to multiply them. 18 times 4 divided by 36 is 2. They're all just numbers. So I simplify. If they were letters, I wouldn't have to do that simplification step unless they matched on top and bottom, because we would just be using numbers here. Okay, this next one, I was going to make you do on your own, but there's a piece of exponent rules I think we might have forgotten, so I want to do it with you. When I'm condensing, the first thing I always do is what? Condense. Okay. I take the power and I put it to the outside on the exponent. Now, there are 2 things in this parentheses, so please be sure to look at the notation that I'm about to use. This is ln, or natural log of x to the 5th, minus the natural log of xy squared. I had to add another set of parentheses because I am squaring both x and y. If I were just to put it out here, be very confusing notation. If I were just to put it behind the y, that would be only squaring the y. I need to square both parts. So I would condense it. X to the 5th on top, x squared, y squared on bottom. Why are they both now squared? I'm distributing, air quotes distributing. It's not really distributing, but it looks like it. This 2 to both pieces inside that parentheses. That's the power to a power rule of exponents. There's one more step of simplification here. Do you notice it? What is it? Yeah, we're dividing these 2 bases right here. What's x to the 5th divided by x squared? X to the 3rd? Yep, because 5 minus 2 is 3. Remember, when you're dividing the exponents, you subtract the powers. And voila, we have condensed it. So much algebra today. Isn't this great? Last thing, thank you for your honesty. Last thing is called the change of base formula. I've said this multiple times today, but your calculator only has a button for base 10 and base e. So you're going to have a natural log button and you just have the common logarithm button. So if you wanted to evaluate a logarithm that you weren't able to do in your head because it's not like similar bases, like it's not like a power of 2 and a power of 2 or a power of 3 and 3, something like the example A where you're using 5 and 7, those are not in base pairings of each other. Right? Like there's no base that I could be able to get them in. We can use what's called the change of base formula. If you're wanting to evaluate this logarithm, you would actually just divide the common logarithm of the base and the of number. Meaning, if I wanted to know the logarithm base b of a, and they weren't something I can do in my head, I could, in my calculator, make the fraction logarithm of a divided by logarithm of the base, the common logarithm, or like the natural log version of that, so meaning you can pick either the log or the natural log button when you're doing this. Either way, as long as a is over b with different logarithms, it will evaluate approximately what the number is. It won't come out to something pretty because the pretty ones you can do in your head. This will be a decimal. So if we were to do a, which is log base 7 of 5, we could do, log of 5 divided by log of 7 in our calculator. It does ask me to round to the nearest thousandth. How many decimals is 1,000? 3. So if you do that in your calculator, remember the log button is above the, what's that button called? The on button. It's a couple above the on button. It's on that side. It's like 4 above it is the log button. Or you could choose natural log as long as you stick with the same thing. Log of 5 divided by log of 7 is approximately 0.827. Now again, because we're approximating this answer and we rounded it, I would like for your equations, your equal sign to be wavy. That means approximately equal to. And again, we can't do this one in our head because 0.4 and 8 are not of the same power family, for lack of a better word. So we do log of 8 divided by log of 0.4. We'd ask our calculator nicely to calculate that for us. We'd get negative 2.269 approximately. So in a pinch, if this is on the calculator portion of the quizzes or tests that I'm giving you, you can use the change of base formula for the nice pretty ones on the front. They'd give you a nice pretty number. But we only use the change of base formula for ones that we can't do algebraically in our head. Or I'm going to request that that's how we do it.